Okay, so here we go. We're going to review the sums of geometric sequences. Sums is plural because we're going to talk about two different types of sums, partial sums and infinite sums. The first thing we're going to do is we're going to consider the expanded partial sum of a geometric sequence. The formula for the partial sum is not given, but analytically, the expanded form of a partial sum, this means the sum of the first n terms of a geometric sequence, which we see as a sub 1 plus a sub 1 r plus a sub 1 r squared plus a sub 1 r cubed plus dot 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 plus a sub 1 r to the n minus 1. What we need to notice is that there are n terms there. People get freaked out because they think, oh, there's only n minus 1 term there. No, there's n terms there because keep in mind, this is that plus 1. Okay, so there are n terms there of that partial sum. That's the expanded form. All I'm going to do now, and the reason why I know how to do this is because I've done this multiple times before. They have given this demonstration in the textbook that we have. They have not given the demonstration on, it was a brief discussion on the infinite sum. Talk more about that later, that we're going to go through, and you are going to follow the infinite sum discussion well, I guarantee you. So what I'm going to do, because I know how to do it, because I've done it before, is I'm going to take and I'm going to multiply equation 1 by r. And this is equation 1 right there. I've denoted that as equation 1. What I'm going to do is divide that by, or multiply both sides by r. And keep in mind, this is an equation. It's not even identity. It's a true equation. This sum is equal to these things added together. It just so happens that we don't know how many n's there are, what n is. Doesn't matter. That is an equation. And the multiplication property of equations of real numbers says that I can multiply an equation by any number and not change its value. And that's exactly what I've done. I've multiplied both sides by r, and this is going to give us equation 2. And you notice I multiplied this partial sum by r, and now I'm going to multiply each of these terms by r. This is what I'm going to do. I'm going to multiply both of those terms by r. If I take r, do the distributive property, if I take r and multiply by a sub 1, what do I get? I get a sub 1 r, right? And I'm going to explain why I slid it over. I slid it over because I want it to match up with this a sub 1 r. If I take r and multiply it to a sub 1 r, what's r times r? R squared. That gives me a sub 1 r squared. What is r times a sub 1 r squared? A sub 1 r cubed. And what you need to notice is that these terms here are matching up between this equation and this equation. Okay? Now I'm going to multiply r to a sub 1 r to the n minus 1. What is r? As a side note, what is r? I think I can put it in here. What is r to the n minus 1 times r? Using the law of exponent number 1, if I multiply like bases, I add exponents. So r times r to the n minus 1 times r is simply, that's a positive 1. It's going to be n minus 1 plus 1, which was r to the n. So when I multiply by this, that guy goes there. And what I'm going to do, just so I can continue lining things up, I'm going to look at the previous term. Now, I could look at the previous term here. I don't really note that. I really don't write that in my expanded form. But the next term, the previous term of that will be a sub 1 r to the n minus 2. Multiply by r, and I'm going to get this term right here. And so now I have something to match up with this term. Very cleverly, what am I going to do now? I'm going to do this subtraction problem. Equation 1 minus equation 2. So I'm going to take all the terms from equation 2 and subtract them from equation 1. And I'm going to come up with this guy right here. I'm going to do equation 1 minus equation 2. Well, what does that give me? That gives me S sub n minus R S sub n. That's where this creature comes from. This is S sub n minus R S sub n. And I don't have anything to subtract from A sub 1, so A sub 1 just drops down there, yay or nay. But check out this. What's A sub 1R minus A sub 1R? Gone. What's A sub 1R squared minus A sub 1R squared? Gone. What's A sub 1R cubed minus A sub 1R cubed? Gone. Dot, dot, dot. What's A sub 1R to the n minus 1 minus A sub 1R to the n minus 1? Gone. And so what do I have left? This should be a minus sign. Yes, because I don't have anything, so I have 0 minus that. That should be a minus sign. And then that is going to, yeah, that should be a minus sign, not a plus sign, because I don't have anything minus that. So that's an error in your notes. Make sure you fix that error. I could have gone positive, negative. Make sure that you denote that that is indeed a negative sign. Okay. Got a little error I made in the notes here. And so now that gives me this equation right here. This is my new equation. Look what I've done. And I know where I'm going. I know what I wanted to prove. I wanted to prove the partial sum. I got to walk away. I can't walk away because I'm videoing here. I wanted to prove that formula that I gave you yesterday for the nth partial sum. So what I did here with these terms is I just factored in S sub n now, distributive property. And this is going to be S sub n times 1 minus R. Look what I'm going to do here. Well, the first thing I'm going to do a couple things. I'm going to factor the A sub 1 out. If I factor the A sub 1 out of those terms, I'm going to get A sub 1 times quantity 1 minus R to the n. And now I'm going to divide by 1 minus R, and that gives me the formula for the nth partial sum for a geometric sequence. Yes, sir.
So yesterday you, for that equation, you put A sub 1 times 1 minus R to n over 1 minus R. So shouldn't it just be A sub 1 times 1 minus R again, and then all of that divided by 1 minus R?
You mean like this?
Yeah.
Yeah.
Because yesterday you had to turn things around the fraction and you multiplied A sub 1 of that.
Yeah, and that would be okay. You could do that.
Yeah.
Mathematically, yes. You could absolutely write it that way. Yeah, you could actually do this.
So that wouldn't change the answer.
That's not going to change anything. That's not going to change the formula at all. Okay? So this is the formula for the nth partial sum. First term times 1 minus r to the n divided by 1 minus r. Okay? Did that yesterday. Get your calculators out.
Okay.
I'll have a little activity here just to help you what's going on. I'm going to pause the video. I think so. Here's what I would like for you to do. We're going to look at 5. We're going to look at 4 geometric sequences, and we're going to name R. We're going to consider the following. We're going to find the first 5 terms. We're going to graph those terms. We're going to name R, and then we're going to answer the question that follows. So what I would like for you to do is put this geometric sequence in your calculator and find the 5 terms. The first term, the second term, the third term, the fourth term, the fifth term, and find R. Right off the bat, before you do that, I'm going to ask Harrison, look at that equation and tell me what R is, dog.
R is 1/3.
Thank you. Okay, I'm going to give you a moment. I'm going to pause the video, give you a moment to find the first 5 terms. Okay, so you've had time to find the 5 terms. Morgan, can you give me the first term? I think it's 2.
I think it's 2.
Can you give me the second term? 2. Oh, I bet you $5 to a donut that you have the wrong equation and that you didn't use appropriate parentheses. I'll bet you did. We'll check it. Molly, can you give me your second term? So, as a fraction, Preston, what's 2/3? And if I notice, if I believe Harrison as I do, if the common ratio is 1/3, I can get the next terms pretty easy. 2/9, 2/27, 2/81. Okay? So, golly gee, let's graph them. I think we're going to be able to graph them fairly easy. You're not going to get them exactly, but the first term is 2. Then it goes to 2/3. I think I can use, I think I'm going to use purple. So I graph the first term 2. The second term is going to be 2/3. And then I go 2/9. And then they just keep getting, oh, my line is crooked. Then they keep getting closer and closer. And then do they ever really, trying to do this, do they ever really get to that x-axis? No. You need to realize that they never really get to the x-axis. But those are those terms. It's like an exponential. So now the answer to this question is pretty easy. And this is the question. As n goes to infinity, I think it's clear that a sub n, i.e. this sequence of numbers, is approaching what? 0. We have problem number 1 finished. Let's go to problem number 2. And before we do problem number 2, and what's really nice, you can use your calculator, but if you have the correct R and the correct first term, you really don't even need your calculator. It's pretty simple. Okay, so I ask a human being, what do you think R is, Lexi? For number 2, what do you think R is? 2. You are correct. R is 2. What do you think the first term is, Annie? 5. The first term is 5. Because if I put n minus 1 and n minus 1, it's 0. 2 to the 0 is 1. 5 times 1 is 5. And now all 10, 20, 40, 80. Those 5 terms should be very straightforward. I'm going to plot those fairly quick. Here we go. 1 is going to be 5. 2 is going to jump up to 10. 3 jumps all the way up to 20. Certainly out of scale here. 4 jumps up to 40. And then 5 jumps all the way up to 80. And we see that it is an increasing, the corresponding function of real numbers is an increasing exponential. This is a discrete function, it's not continuous. But we know that the terms are increasing, so we can answer this question pretty easy. As n goes to infinity, a sub n, which is 5 times 2 to the n minus 1, goes to, hands up, infinity. And you're going to see why this is going to be important that I put these 4 problems there. We're going to go to the next problem. I think it's found on the next problem. Oh, I even helped you out here on number 3. Because if you look at number 3 just for a moment, if you look at 3, I'm going to pause the video and let me go to the video. Sometimes it might not be easy to see that r is indeed negative 1/4. Let's find a couple terms and see if we can convince ourselves that r is negative 1/4. Let's put n equals 1 in. If I put n equals 1, negative 1 to the 1 power is negative 1. 1/4 to the 1 minus 0, what's the first term? Negative 3. The first term is indeed negative 3. If I put the second term in, what's the second term? If I put n equals 2 in, the negative 1 squared is going to make the thing positive. Okay, so I know it's going to be positive. If I put 2 in, what's the second term going to be? I'm going to have 1/4. I think it's simply going to be 3/4, right? Let's find one more term without using r. If I put 3 in, negative 1 cubed is positive or negative. Negative, let's write that negative down there. And if I put 3 into the n minus 1, I have 1/4 squared, and 1/4 squared is 1/16, yay or nay, but it's going to be times a 3, so this is going to be 3/16. And I think at this point, I think you can kind of see that, yes, the r is negative 1/4. Negative 3 times 1/4 is negative 3/4. Negative 3 or 3/4 times negative 3, negative 1/4 is negative 3/16. Times negative 4, it's going to be positive, and it's going to be 4 cubed. The next term is going to be negative 3, 4 to the 4th. If I graph those bad boys, let's graph those bad boys. We'll graph them in. The first term is going to be negative 3. What's the second term? 3/4. The third term is negative 3/16. And we've been looking at these for quite some while, and we can be confident that what's happening to those terms, they are alternating, but as they alternate, what's going on with those terms? They are approaching 0, so we can answer this question pretty good. As n goes to infinity, this particular geometric sequence does indeed go to 0. Okay? Let's do one more example here. Let's do example number 4. Bam! Right off the get-go, the r now should jump out at you, because I don't have that negative 1 in parentheses. I have the basic formula for the geometric sequence. In r, jumping right off the page, Can you tell me R? I hate to call people out on the video. Can Carter, can you tell me R? I just did. I don't want to do it. Bam. -3. Can you tell me the first term, Mr. Wilhite? 2. Because if n is 1, 1 minus 1 is 0, -3 is 0 is 1. So this is going to be 2. I have the correct first term. I have the correct R. Now I'm just going to flat all -6, all 18, all -48, all whatever that is. Positive 3 times 48. What is that? Oh, so I don't know how to multiply. I can do that. I don't. Oh, yeah. So this is wrong too, then, doesn't it?
Yeah.
That's funny. So somebody tell me what it is. Positive. Okay. Well, let's graph these rascals. We'll graph these in blue just for giggles. First one is 2. Way down there. -6. A little farther out. 3 is 18. Jumps up here. 4 is -54. Jumps out there. And then 5 is what? Way up here. Oh. Ooh. Oh. As n goes to infinity, where does the nth term go? I'm going to pause. I say this in hesitation. As n goes to infinity, yes, this thing, let's just say that goes to positive and negative infinity. But I can tell you this. As n goes to infinity, a sub n, which is equal to 2 times -3 to the n minus 1, does not go to 0, does it? No. And I can also say that as n goes to infinity, a sub n, I could look at this. I'm going to do this down the road. The absolute value of all those terms, I can take the absolute value of those terms, correct? Because those terms are numbers. So I can take, and that does indeed go to infinity. Okay? I am DDing, right? So here's a question to you. Here's a question. You ready? Or I'll let you. Okay, so here comes the question. Okay, so here are the statements. Consider the statements A, B, C, and D. A, and these are statements that grouping the statements that we just created. Okay, I know there isn't a question. Yeah, I was made a mistake and I forgot about my notes. Bam. Oh, here's the difference here. As n goes to infinity, a sub n is equal to 2 times 1/3 n minus 1. That goes to 0. And keep in mind, doesn't r to the n, r here was 1/3. If n goes to infinity, doesn't 1/3 to the n go to 0? Yes. Doesn't that go to 0 as well? Okay. As n goes to infinity, 5 times 2 to the n minus 1 goes to infinity. And what does r to the n? I'm not talking about r to the n minus 1. I'm just talking about r to the n. Does r to the n go to infinity? Yes, it's exponential. So what I'm going to look at here in a moment is just where r goes. Not where the nth term goes, because I clearly determined these 4 statements right here, this part of these statements. I've clearly, and everybody was good with this. Now I'm going to specifically look also where the r to the n goes, as n goes to infinity. So look at this guy right here. As n goes to infinity, this geometric sequence goes to infinity. 2 to the n goes to infinity. I'm going to look at this guy right here. As n goes to infinity, the sequence goes to 0, and r, which we discovered was -1/4, that goes to 0 as well. And then we did discover on the last one that this guy here went to positive or negative infinity. But if I just look at this nth term goes to positive infinity, if I just look at the r, which was -3 to the end, that's going to 0. No, that's going to infinity. But that's actually going to, let's see, it's -3. That's going to infinity as well. I think that's going to negative infinity. That r, which is -3 to the end. So it's going to go, ooh, that one looks like this. Y is equal to -3 to the x.
Yeah, that one. Yeah, that's it's not in the negative, it goes to 0.
So this is going to be positive and negative infinity right here. Certainly not 0. That was a typo. I wrote these up early in the morning. It was during the first cup of coffee. Yeah, they had a lot. But this, I wrote this up in the morning while I was getting. So, okay. So here's your question. Here's the question. It follows that. I don't even think I wrote it as a question. Oh yeah. I didn't write it as a question. I wrote it as a statement. It follows that as n goes to infinity, r to the n goes to 0. Okay, here's my question. True or false is the question, true or false. If n goes to infinity and r sub n goes to 0, can you see that this partial sum as n goes to infinity and r sub n goes to 0, those are my two conditions, can you see that this goes to a sub 1 over 1 minus r? This is going to be a little bit more easier for Carter and Taylor because they've had a formal discussion of limits. But check this out. And we did this, think about what we did in Kerbillion. If n goes to infinity and this guy right here, r to the n goes to 0 as n goes to infinity, we did that a lot with just the rational functions. This guy here is 0 as n goes to infinity. That goes to 0. What's left? The only thing left on top is a sub 1. 1 minus r is 1 minus r. And the most important question then, when does r to the n go to 0? When does r to the n go to 0? If I look at my examples, when did r to the n go to 0? Up here. Well, it's when r was 1/3 and when r was -1/4. What do you know about 1/4 and -1/4 and 1/3? Those are numbers between -1 and 1. Wouldn't that work? Wouldn't this formula hold for any time that r was between -1 and 1? That formula would work because that guy is going to 0 out. If you have a geometric sequence where r is between -1 and 1, then this partial, we don't call it a partial sum anymore. Why isn't it a partial sum? Because n is going to infinity. That's what we call an infinite sum. How do you write an infinite sum? You're going to write an infinite sum as n goes to 1 to infinity. Because how many things am I adding up? Infinitely many terms. How do you write that in expanded form? You're going to write that in expanded form. A sub 1, a sub 1r plus a sub 1r squared plus ... a sub 1n minus 1. That's the nth term plus a hell of a lot more. Because I'm starting the nth term, but it's going over, and guess what that gives me? This is the first time you've experienced this. What's a sub 1 over 1 minus r? What do we call that? Fundamentally, what do we call a sub 1, 1 minus r? A what? It's an infinite sum, but what is that infinite sum? In its basic form, that infinite sum is this is only true when R is between -1 and 1. And I'm going to tell you something right now. This is only true when R is between -1 and 1. I will tell you, I'm honest to you about that. We will use this fact at least half of what we talk when we do talk about calculus series. We're going to use this fact right here. So I have a question for you. And I'm going to pose this question. Find, if possible, number one, Skinner. What's the sum? Doesn't exist. We're just going to say, dude, doesn't exist. Does not exist. Why not? This sum does not exist since R is greater than 1. Okay. Okay, Jack, go for it. What's this sum?
I got 28 over 4.
Oh, you mean it's first term over 1 minus... You mean it is equal to 7 over 3/4? Oh, you mean it is 28 thirds? Yes. Done, you should.
We're talking about this, but is there a way to put your table into, like, whatever I did, like,
Yeah, I don't know. Maybe. I don't know. Here's another question for you. Find the infinite sum of 9 n equals 1, 3 other than 1, have 8 minus, good. When do we get out of here? 9:55. I have 20 minutes. I want to get this homework graded.
10:50.
Okay, let's see here. All we need to know is what the first term is 3. R is -1/2. 1 minus -1/2 is going to be 1 plus 1/2, so it's going to be 3 over 3/2, which is equal to 6. And Zoe, did you get that? Whoop, good deal.
it's over 3, and then that'll,
Oh, so, and you said 2.
yeah.
You actually said 2. There, I'm throwing you under the bus. You said 2, because you multiply by 2 over 2. 2's cancel, whoop. 3's cancel, and you get 2. Okay? I'm going to process this video. What I'm going to do is I'm going to ask you to do a